In this video, we want to calculate the lattice energy for the formation of rubidium chloride. This is an energy diagram. Going up represents an increase of energy. I will remove this in subsequent slides. And we're looking at the lattice energy. Lattice energy can be defined as a formation or as a dissociation of a crystal. Okay? Here I'm writing it as the formation of a crystal where I have the ions separated in the gas phase. And if you think of Coulomb's law, if they're in the gas phase, they're far away from each other, so their energy of interaction is negligible. And then they come together and they form the crystal, which has very strong energies. We often describe the lattice energy as a dissociation, which is the opposite process. And remember, the change is the final state minus the initial state. So if I go from here to here, this number is lower than this, so this minus this is a negative value. So energy is lost in formation. And if I look at the dissociation, energy is gained. And the energy is the same, it's just the difference in direction. Okay, now, the idea of an energy cycle is if I can find more than one way to make something, okay? So one other way of making a substance is through its standard enthalpy of formation, okay? That is, if I create the rubidium chloride from its constituent elements in their standard state. Chlorine is a diatomic, rubidium is a solid, okay? And this is the enthalpy of formation. Notice that this is a molar value. This is the energy change per mole. So I can easily have a half a mole of chlorine gas. That's like 3 times 10 to the 23rd molecules. Okay? And it's important that we recognize the difference between an enthalpy of formation and a lattice energy. Okay? One of them is from the separated ions. The other is from the atoms in their the elements in their normal standard state. Okay, now the first thing we could do is we could say, okay, I have chlorine as a diatomic, I need a monatomic. The chlorine molecule has a single bond. So from the bond dissociation energy, I can calculate. Now, every time I break a mole of chlorine gas, diatomic, I make 2 moles of chlorine atom. Atomic chlorine, okay? Therefore, I'm only going to break a half a mole, so I have half the bond dissociation energy, okay? Remember on bond dissociation energies, if you have more than one bond in a molecule, you have to look up the Lewis dot structures to recognize what's going on. Okay, now I've got chlorine as a gas and rubidium as a solid. I need rubidium as a gas and as a cation. So the next step is logically to sublime, convert to a vapor, the rubidium, and this is its enthalpy of sublimation, okay? Now, the enthalpy of sublimation for this step, going from a solid to a gas, notice the chlorine hasn't changed, is actually its enthalpy of formation, okay? And enthalpies of formation may be positive or negative. The table's in the back of your book. But the enthalpy of sublimation must be endothermic. It takes energy to take something from a solid phase and put it into a gas phase. Okay? So these first 2 steps are endothermic. We're adding energy to the system. Okay? Now, now I need to make rubidium as a cation. Okay? If we go to the ionization potential, that is the energy, the first ionization potential is the energy required to move an electron from a neutral atom. And that's what we're looking at here, the first ionization potential. And this is also always an endothermic process. In other words, in the neutral atom, the electron is in an orbital, and I've now kicked it off the orbital. Okay? That takes energy, endothermic. We've added energy to the system. Okay, now I want the electron affinity of the chlorine. The electron goes to the chlorine, and this process may be endothermic or exothermic. In the case of chlorine, it is exothermic, and 349 kilojoules is released to the environment. Now what I have here is the ability to look at enthalpy as a state function. And I want to calculate the lattice enthalpy, and I know the enthalpy of every other step, okay? So I could say that if I go from the start here, step 1 goes from these as in their elemental state to rubidium chloride. Or I could do the second path. First, I'm breaking the bond of the chlorine, then subliming the rubidium, then removing an electron from the rubidium, then moving the electron onto the chlorine. Now I have rubidium as a cation and chloride as an anion in the gas phase. They come together and form rubidium chloride. So this energy must equal this energy. Okay, so step 1 must equal step 2, 3, 4, 5, and 6. And I know the value of all the steps except for step 6. So all I have to do is solve for 6. And before I move on, realize some of these are negative values. Okay, this is a negative value, but I'm adding the energy change of an exothermic step. Okay, so step 6 would equal 1 minus 2 minus 3 minus 4 minus 5. And I now can plug in my values, okay, recognizing that some of these are a negative of a negative. And I come up with the lattice energy, the lattice enthalpy for the formation of rubidium chloride. And if you were asked for the enthalpy of dissociation, which is the opposite process, it would be a positive 692.3 kilojoules per mole. Now in the next slide, we're going to solve this via Hess's law method. And I hope this all helps you out.